Welcome back, everybody. Today we're going to be talking about doing problems that are in parallel and in series, when springs are in parallel or series. Alright, springs in parallel. When springs are in parallel, you can add the values of the spring constant, and this will give you the effective spring constant of the system. So this is pretty easy. This is, for example, when something is hanging by two different springs, or two same springs, or three springs, or four springs. Whenever they're in parallel like this, they're in parallel with each other, then we call this springs in parallel. So for example, if let's say this K1 is equal to 10, this K2 is equal to 30, and this K3 is equal to 50, we can treat this the same as if it was oscillating from one spring. That was a total of 10 plus 30 plus 50. So this would be the same as this K being equal to 90 Newton per meter. Okay, so it's pretty simple. Whenever we have springs in parallel, we can just add up the K values and then we could treat the problem very similarly. Let's try an example though, just in case it might be a little confusing. So two springs are in parallel that each have a spring constant of 200 Newton per meter. How much mass must be connected in order to stretch both the springs 1.5 meters? So that means this one's 200 Newton per meter, and then this one's 200 Newton per meter. And like I just said, we could treat this as if it's just one spring oscillating 1.5 meters. Oh, it's not oscillating actually. In order to stretch it 1.5 meters. How much mass? Oh, we need to find what the mass is. Okay, so we need to know this spring constant is going to be the same as both of these combined. So this would be 400 Newton per meter. And we want to know what mass would this have to be in order for this to stretch 1.5 meters in order for it to get to its equilibrium position. So all we should know for this is we have a force of gravity going down and force of the spring going up. So we have to try to set these two equal to each other. So we have force of gravity is equal to force of the spring. And the force of gravity is mass times 10. And the force of the spring is going to be the K value of 400. And X, we want it to stretch 1.5 meters. So now, if we plug this into our calculators, we should be able to get what M is equal to. Divided by 10. And we get 60 kilograms. That's a pretty heavy mass. Heavy mass? All right, simple enough. Let's try another one. An object suspended from a spring exhibits an oscillation of period t. Okay, a little bit different because it's a variable. Now the spring is cut in half and the two halves are used to support the same object. What is the new period of the oscillation? Okay, so this one is actually a little bit complicated. So let's look at this. So what we have here is we have this spring and there's this mass here, M. What happens when you cut off this spring is that the K value changes. So it might seem like, oh, it's the same spring. Why is it that when you cut this in half, and it's not as long, does the K value change? And the best reason for this is if you think of a rubber band, if you were to shorten a rubber band, you should know that if you stretch it the same amount, it's going to be a lot more stretchy. Because it doesn't have as much room to elongate or to compress, compressing it or elongating will make it a lot harder to do. So it becomes a lot stiffer. So when we cut this in half, that means this K value will double because it's cut into half. So now, what it says, cut in half, and the two halves are used to support the same object. So it's now we cut in half, but it's also parallel. So that means this is going to be the same as this being 4K of the original value. And now it's going to oscillate back and forth. So we know that T is equal to 2 pi square root of M over K, and this K should be equal to 4K. So this is what it should be equal to. The period, the period should change. What is the new period of the system? So if this K value changes by a factor of 4, that means we're going to have this side of the equation change by 1/4. That means that this side of the equation has to also change by 1/4. So the new period would be equal to period times 1/4, a square root of 1/4, or that means period over 2. Hope that makes sense. Watch it again if it was confusing, because it was a little confusing. Okay, now let's talk about this, and this is where it gets a little bit more complicated. So springs in series. So this is what happens when multiple springs are attached to one another. So this is one spring here, and then this spring is attached to another spring, and then we're going to talk about how this is going to be different. So what happens in this kind of situation is the K total or the K effective here. How that is going to change is we're going to do, if you've ever done any electricity or magnetism in physics, it's similar to this when it comes to when it's in series. So we have the 1, I like to say K total is equal to 1 over K1 plus 1 over K2. So this is what we now need to do in order to find what the K total is going to be. And what you're going to notice is when they're connected like this, their stiffness or the K value is going to decrease. And the reason why it decreases is since it's longer now, it's able to stretch more or elongate more or compress more without it being as stiff. Kind of like that same example I gave with the rubber band. If the rubber band became a lot longer, it's a lot easier to now stretch it. I hope that makes sense, but all you really have to know is this formula here. Okay, and let's look at some example problems to figure this out. So we have two springs are in series that each have a spring constant of 20 Newton per meter. So this spring constant is equal to 20 Newton per meter, and then this spring constant here is equal to 20 Newton per meter. If I was 0.5 kilogram mass attached to the bottom of the series, how much in total will the spring stretch? Okay, so first we have to find what the K total is. So we should know again, 1 over K total is equal to 1 over 20 plus 1 over 20. How I like to do this is I like to just do 1 over K total is equal and then plug this into my calculator. So I'm going to do parentheses 1 divided by 20 plus parentheses 1 divided by 20. And now I get this answer of 0.1. What I like to do now at this point is I'm going to find the inverse of these two. And so I'm going to put 0.1 to the power of -1. And then what that gives me is to 10 Newton per meter. Okay? And I hope that makes sense also mathematically. If we know 1 over 20 plus 1 over 20 gives us 2 over 20, which is 1 over 10. So that means K total would be 10. So these two springs in series like this is the same as the K total being equal to 10 Newton per meter. And if we have a 0.5 kilogram object, we want to know how much it will stretch the spring. So we're going to try to find that equilibrium position. And remember that equilibrium position, force of gravity, is equal to force of the spring. So let's figure this out. Force of gravity equal to force of spring. Force of gravity is 0.5 times 10. Force of spring is going to be equal to K total, which is 10 times x. And let's find this. It's going to be 5 divided by 10, 0.5 meters. Okay, so it still shouldn't be too hard, but maybe it's slightly more difficult than springs in parallel. Now let's look at this. 3 springs with a force constant 10 Newton meter, 20 Newton per meter, and 40 Newton per meter are connected in parallel to a mass of 0.2 kilograms. The mass is then pulled and released. Find the period of the motion. Okay, so what we have is we have 3 different springs. We have 1, and actually let me try to draw it a little bit better. I'll draw it to the right here. So we have this 10 Newton per meter, so it's very loose like this. And then we have this 20 Newton per meter, which is a bit more stiff. And then this 40 Newton per meter, which is very stiff. Okay? And they're all of these are carrying this 0.2 kilogram object. Let me do this 10, 20, and then 40. So again, what we're going to do is we're going to try to find what the total K is with all of these combined. So what I'm going to do is 1 over K total is going to be equal to 1 over 10 plus 1 over 20 plus 1 over 40. So now I'm just going to put this all into my calculator. Parentheses 1 divided by 10 plus parentheses 1 divided by 20 plus parentheses 1 divided by 40. And then I'm going to put that to the power of -1. And then what I get is the K total is equal to 5.71 Newton per meter. Okay. Find this period of the motion. So we now know that period is equal to 2 pi. The mass is 0.2 kilograms, times the K total, which is 5.71. Now let's put that into our calculators. Square root of, 2 pi times square root of 0.2 divided by 5.71. And we should get around 1.18 seconds. Okay. All right, so let's look at this one. This one could be a little bit confusing. So it says two identical springs have a K value equal to 20 Newton per meter. A 0.3 kilogram object, a mass, is connected to them as shown in the figures, two figures. Find the period of motion for each system. Ignore frictional forces. Okay, so A looks weird, but B looks pretty simple. We can just see we have two springs in parallel, 20 and 20. So we have a K total of 40 for part B. So all we can do is find the period. For part B, we could just do T equals 2 pi, the mass, square root of mass, 0.3, divided by K total, which is 40. Okay, so these are in parallel, so again, we just add them together. Now we're doing 2 pi times square root of 0.3 divided by 40. And we should get around 0.54 seconds. But now, let's look at A a little bit. This might be a little bit confusing. Okay, so if you were to look at this, and if you want to pause it to try to figure out to do that. But what happens is, if you're to notice this, let's say the ball is over here. If the ball is over here, then that means this is really squeezed, and then this is really elongated like this. But what would happen is this spring here, I'm going to call this 1, will be pushing it this way. And then this spring here will also be pulling it this way. Same thing if it's on the other side, just the opposite thing. This will be very squeezed, pulling it over there. And then this one will be elongated, pulling it also in the same direction. So what we notice is, even though it's like this, it's acting the same way as a parallel spring. So we can treat this the same way as a parallel spring, and the period will be the same thing, 0.54. All right, guys, thanks for watching. Next time we'll be doing some multiple choice problems, so I hope to see you with that. All right, see you next time. Bye, guys.